Welcome to Ask and Learn.
Hi there. So for this problem for part A, we are asked to calculate the rate for spontaneous transitions between the states n equals to 1 and n equals to 0. It states of a simple harmonic oscillator carrying a charge and the charge of an electron E. We need to take the mass of the oscillator to be equal to the mass of an atom of some typical ion molecule, and the restoring force constant C to be 10. So the restoring constant C is equal to 10 to the 3 joules per meter square. Now, for this problem, we start with the equation 8.43, that is the transition rate. So we will have that the rate is equal to 16 times pi to the 3 times the frequency to the 3, and this divided by 3 times epsilon sub 0 times Planck's constant times the speed of light to the 3. And this, the magnitude or the absolute value of the integral from minus infinity to positive infinity of the wave function, the conjugate of the wave function at the first state times the charge times x times the wave function in the second state n equals to 1, and this integrated over x. We take the magnitude of this, of the absolute value, and then we take the square of this. And with the frequency is going to take the value of 1 divided by 2 times pi times the restoring force constant C divided by the mass, and this elevated to 1 divided by 2. Now the integral in the expression for the rate, we can do the following change. That is that U is equal to the restoring force times the mass, and all of this elevated to 1 divided by 2, and this times x, and this divided by h elevated to 1 over 2. So with this, we will have the following. 2 times the charge of an electron times a sub 0, where these are normalization constants, times a1, and this the integral from 0 to infinity of the exponential of minus 1 divided by 2 times u squared times x times u times the exponential of minus 1 divided by 2 times u squared, and this integrated over x. So in here, what we can do is to take out from this what is a constant in here. So we will have that this is equal to h divided by the square root of the restoring force times the mass, and this the integral from 0 to infinity of u squared times the exponential of minus u squared integrated over u. Now with this, we can just obtain that this integral is 1 divided by 2 times a sub 0 times a1 times h bar times pi divided by the restoring force times the mass, and this elevated to 1 divided by 2. Now the normalization constants a1 and a2 are determined by the following. So we know that this 1 should be equal to a sub 0 squared, the integral from minus infinity to plus infinity of the exponential of minus u squared integrated over x. So from this, we know that this should be equal to a sub 0 squared times h bar times pi times this elevated to 1 divided by 2, and this divided by the restoring force times the mass elevated to 1 over 4. And something similar for the other normalization constant, a1. So we will have this to the square, the integral from minus infinity to positive infinity of u squared times the exponential of minus u squared integrated over x. That will be 1 divided by 2 times a1 squared times h bar times pi elevated to 1 divided by 2, and this divided by the restoring force times the mass, and this elevated to 1 divided by 4. Now, solving this last for the normalization constant, the expression for P then becomes 1 divided by 2 times the charge of an electron, and this times 2 times h bar elevated to 1 divided by 2, and this divided by the restoring force times the mass and elevated to 1 divided by 4. Now, putting this and the expression for the frequency into the rate gives finally for m, remember that m in this case is 10 times the mass of a proton, then the restoring the rate art is equal to the charge of an electron times the restoring force, and this divided by 3 divided by 2 times 4 times pi times epsilon sub 0 times the speed of light to the 3, and this times the mass to the square. Now, with this, we can substitute all of the numerical values. So we will have, in the denominator, we have 1.5 for the 3 divided by 2. And the speed of light to the 3, we know that the speed of light is 3 times 10 to the 8. And to the 3, of course, and this times the mass we know that is 1.67 times 10 to the minus 26 to the square, and in the numerator we will have the charge of an electron that we know is 1.6 times 10 to the minus 19, and that to the square, and the inverse of 4 times pi times epsilon sub 0 that is in the denominator, but we can write the inverse of that, is what we know as Coulomb's constant, and that is 9 times 10 to the 9, and this times the restoring force that we are given is 10 to the 3. So from this we obtain a rate of 20 seconds to the minus 1. So that's a solution for part A of this problem. Now for part B, we are asked about, so we are told that from the transition rate, estimate the average time required to complete the transition. This is the lifetime of the n equals to 1 vibrational state of the molecule. So the lifetime, we know that that is just the inverse of the rate that we just have obtained. So that will be 1 divided by 20 seconds to the minus 1. So from this, we obtain a value of 0.05 seconds. So that's the solution for this problem.